becomes of the order, okay, it becomes of the order of the whole system, of the whole number of particles that there are inside the system. Now, why we were wrong in the first place, what we needed to correct, and how it's related to this condensation transition. Okay. So, think about it in the following fashion. The number of particles is extremely large. Okay? So we are looking on the number of particles, which is approximately Avogadro number of particles. Okay? So this is 10 to the 22. Okay? It basically means almost infinite. It's huge. Now, we calculated this total number of particles n by summing up or integrating over all the different particles on the energetic spectrum, right? We assume that there is some function, and the total number of particles was the integral, okay, was the integral over this function, which is basically the area below the curve, and the curve is provided by the average number of particles at specific level epsilon. Now, so if we're considering that the number of particles at a specific range, okay, so if we have n or epsilon, and we have epsilon plus delta, so the number of particles that are sitting inside this range is the area under the curve. It's the area under the curve. Now, what we eventually obtained with this total number of particles at the lowest level, that there is a very specific point, this epsilon equals 0, so the ground state, where we can say something different, because usually I need some non-zero delta in order to obtain a non-zero area beneath the curve. Because if I'm looking, what is the area beneath the curve if I'm looking on some epsilon prime, okay? So the area is simply 0. When delta goes to 0, the area is going to 0 also, okay? Now, what we obtain is something totally different. We obtain what, but we look on this specific point when epsilon equals 0, right? And we look on the number of particles that sits here. So we start from 0 up to delta, right? And we're looking on this area that sits over here. So the total number of particles that sits on the energetic levels between 0 and delta. Okay? And the result is that if we take delta towards 0, this total number of particles is not going to 0. Okay? This is the conundrum. This is the provocative result. Okay? Usually when you assume that the functions are continuous, this is not the case. Now what happened here is that we look on some specific area or specific region on the energetic spectrum. We take this region to be 0, and we assume that the area also has to go to 0, but it's not what happens, right? So the total area converges to a specific value. Okay. Now this value is not 3, not 2, not 1. This value is on the order of the total number of particles. Okay. We will calculate exactly how many particles are sitting there, right? But this is what happens. The total number of particles that are sitting in this small region becomes not infinite, but it comes on the order of total number of particles. Now, this won't happen anywhere else, because if we assume what happens in the region of delta and 2 delta, okay, and we look only on this region and then we will make it smaller and smaller and smaller, eventually the area will converge to 0. The only exception is the ground state. Now, why it is so? Because everything else is protected.
אמרנו את הטמפרטורה שמפחות, לא? אם אמרנו את זה בטמפרטורה שמפחות מ-TC.
Maybe you can close the window. Thanks.
אבל אמרנו שזה נכון אחרי שהטמפרטורה נמוכה מ-TC, לא?
Yes. This only happens, look, T is smaller than TC. Okay. Now, because when we're looking on what happens at N0, okay, and it is 1 over e to the power beta epsilon, or beta mu minus 1. Right? This is what we are getting, or minus 2. Only so when mu converges, when epsilon goes to 0, epsilon 0, or epsilon 1, 1 goes to 0, and mu goes to 0, this term is dominant over which term? Over N1, which is, and we have shown this, 1 over e to the power minus, beta epsilon 2, 1, 1 minus mu minus 1. So the particles start to condensate over here. And the number of total number of particles that can sit in this limit is bounded only by the total number of particles that we have inside the system. Right? So the system prefers to place particles on the lowest level. There are some amount of particles on the next level, and the next level, and the next level, but they are not huge. They can be big, but they are never of the order of the total number of particles inside the system. Right? So this is the dominant term, and because epsilon 1, 1 is smaller than epsilon 2, 1, 1, it protects, basically the lowest energy protects all the other levels, because the system prefers to occupy this guy first, okay, and then maybe start to occupy the next levels. But the amount of particles that can sit here is infinite, because those are bosons. If there were fermions, then there is a limitation. There is only one particle per state, right? So this is why, for fermions, they pile up on top of each other. Bosons, they pile up in this direction, right? So if you're thinking about how bosons versus fermions, fermions pile up one on top of each other. This is the Fermi behavior. This is why only whatever the interaction between the particles are not important for fermion gas. And for bosons, they are piling up in this direction. This is the only distinction, or effective distinction. Bosons, fermions. All right, so that now we know that we have to treat this specific position differently. We can go and see, well, actually, what happens, how we obtain this. Okay. Question: how to obtain the proper grand canonical potential. And the answer is quite easy, because everything that we have performed is fine except this specific one point at epsilon equals 0. All the integrals that we had, everything was fine. The only thing that was different and have to be treated differently is this point. Okay? So we can basically say the following thing. So we calculate so far the total number of particles inside the system. This is the average number. Now, I'm going to say the following thing. This number equals to Ne, which is the number of particles in the excited states. So all the states except the the ground state, right? This is Ne. plus the average number of particles that sits at the ground state. So, number of particles at ground states, yeah.
It's not go to infinity?
What do you mean identity?
Infinity.
No, it cannot, because the total number of particles is limited. It can't. You're right if the total number of particles can be infinite, but it's not, because I fix the total number of particles inside the system. Right? And this is number of particles at the excited states. Okay. N0 is simple, right? We know what N0 is. So N0 is 1 over e to the power minus beta mu minus 1. Now I can basically say, well, it is 1 over fugacity minus 1, and which is fugacity 1 minus fugacity. Okay. So this is N0. What is N excited? Ne. How can we compute the other stuff? Well, we can return to this representation of the integral and say, we know that we haven't done anything wrong except miscalculating whatever is going at 0. Okay, so there is some sort of a delta function that starts to grow at 0. Right? Something peculiar starts to happen. But everything else, this integration, so the differences between the energetic levels was going to 0. Remember, the effective temperature is 10 to the minus 14. Okay. The function is continuous except 0, but everywhere else it was continuous. There were no huge drop-offs over there. So we can say the following thing. Well, actually, N excited stays exactly the same as we calculated before. Okay. We can just simply say, well, look, the excited part, N excited, is whatever we had previously. Okay, so this is G0 V divided by lambda t to the third F3 halves of the fugacity. Because we treated this integral, and this integral was treated correctly, something wrong was at 0. We treated 0 by including explicitly this N0 over here, but everything else, all the excited states, they're completely fine. So now I can go and finally write the following expression. The average number of particles, N, okay, the average number of particles, N, is G0 V lambda t to the third F3 halves over the fugacity when T is larger than Tc. But when we're crossing this explicit specific temperature and at the specific temperature, what becomes of the fugacity? The fugacity becomes exactly 1. Remember how we obtained this critical point? We said, well, something peculiar happens to this function. At specific temperature, the fugacity is exactly 1. This is how we obtained this limitation and the total number of particles cannot exceed something. So something wrong was happening exactly at 1, right? So we have at T lower than Tc, the following thing. We have fugacity, 1 minus 1 fugacity, or in general, I'm sorry. In general, we have this one, plus fugacity 1 over fugacity. And we have to somehow treat differently this part when we're going below Tc or above Tc. So what is the problem? Where are we stuck? We stuck at the point, right, when fugacity is of the order 1. So we can describe what is the critical temperature. Is when n divided by v multiplied by lambda t c divided by g0 to the third equal f 3/2 of 1. Okay. This is the problem. This is the problem that we know that this is the critical temperature. And what exactly is Tc? How we find it? Well, we know explicitly what is lambda t, right? Let's write it down again. So we know that lambda t equals to lambda tc equals to a square root of m k Boltzmann tc this is 1 over lambda t divided by 2 pi h bar squared. This is lambda t for any t equals to this. So when we have a critical temperature, this is what we have. Okay. So we can put this part inside. Okay. This is the problematic point. Okay. And the problematic point is becoming that we have n divided by v multiplied by, so what we have here, 2 pi h bar divided by m k Boltzmann tc. Okay. All of this to 3/2 multiplied by 1 over g0 equals to f 3/2 of 1. So let's take out the critical temperature out of this expression. So what we obtained that n divided by v multiplied by 2 pi h bar squared divided by m k Boltzmann, all of this to the power of 3/2 multiplied by 1 over f 3/2 over 1 multiplied by g0 equals to dc. Okay, and we have to take everything. Yeah. I'm going to take it over here, 2/3. So this is the expression for the critical temperature. This is the expression for critical temperature. Now, if we go and basically submit here all the properties of helium-4, so for helium-4, we obtain Tc around 3 Kelvin. Okay. Now, if we go to experiment and we cool down this helium-4, we cool it down, we cool it down, we cool it down, and at some point we see something exciting happens. This helium-4 starts to flow below a specific temperature as if there is no friction. Right? When you put a drop of water on a slope, the water will spread around and basically at some point it will stop moving. Right? You put a drop of water, right, on a slope, it will spread around, will start as a drop, and eventually it will spread around and will be smooshed over all the surface. And it will stop because of friction with the surface. Now you do this for a drop of helium-4 and it's not stopping. The drop is continuously, if it's cold enough, if the temperature is below some specific critical temperature, this drop will continuously flow below, and nothing will stop it. And this is a fantastic result. So there is no friction. the idea, or why there is no friction, is exactly this Bose condensation. All the particles are sitting at this lowest quantum level, and in order, what is a friction? Friction is its specific excitements of the system to higher energies and lower energies, and this is why how system loses energy, by getting excited, okay, and releasing the energy to heat. Now, if all the particles are sitting at the lowest possible energy, it's really hard to excite them all, okay, due to some quantum effects. So there are no losses of energies, and this drop of helium-4 will just continuously flow. Okay, it's a superfluid. Why? It's not losing any energy. This critical temperature, so in reality, the critical temperature is 2.17. This is really, really, really close. Okay? This is really close. Now, why the temperatures are different? Because, well, we assume that the bosons do not interact with each other. In reality, they do interact, so it modifies stuff a little bit, but not too much. But generally, there is a critical transition from one behavior to another behavior. Why it happens? It happens because of this Bose condensation. All the particles, or majority part of the particles, sitting at the lowest level, okay, and doing nothing, right? Doing nothing. Friction is particles are getting excited and lose their energy to heat. But if the particles are not excited, then there are no losses of energy, so there is no friction. Okay? Friction is not something that has to happen. It has to happen if it's possible to excite particles and then lower their energies. So, and basically in this process, some energy is lost. But if particles are not excited, no friction. Okay? The same happens for superconductivity. Right? So there is a flow of carriers, charge carriers, such that there is no friction, no resistivity. What is resistivity? Resistance, I'm sorry. In electric circuits, the electrons are trying to make their way through the material, and they're constantly hitting the part of the material. They lose energy because of those encounters. And this is why they stop moving, right? The system is actually heats up, and this is why you have to pump constantly energy to the system in order to overcome this resistance, right? Now, there are specific materials that are superconducting, where charges are flowing without resistance. Why? Again, because they are somehow become bosons, okay? And the bosons sit below the Bose-Einstein condensation. They sit below a specific temperature. They sit at their lowest state, so they cannot lose energy. There is a gap. Okay. So the same happens here. This is critical transition. Yes.
How do you obtain these kind of temperatures?
This or that. I cool it down extremely slowly.
Yeah, but how?
So usually by expanding gas. Okay, so there are several ways to cool down everything, but think about it the following way. When you have a gas, or when you compress it or you release it, the temperature has to cool down. So this is what I do. I either compress it or either release it slowly and slowly and slowly, such that the system starts to cool down. This is the simplest technique. In order to get to lower and lower energies, we have to make stuff more sophisticated. But generally, I have to release the gas, expand the gas slowly.
It's like PV equals NKT.
Yeah, the idea is this PV equals NKT. Okay. It's always like that. This is the simplest idea. Okay. And the moment you control this, you can control that. That's it. But there are much more more modern ways. So, for example, you can cool down single molecules. So there is this lab of Lev Haikovich down the hall. When you, you basically start to bound energies, you catch them up, prevent them from flowing around, and this is how you start to cool it. So basically starting to trap single molecules. It's different. Here you're doing something to the whole gas, but nowadays there are techniques that you can do it for single molecules. You basically start to trap them. What is temperature? Temperature is kinetic energy. So when you prevent particles from moving, okay, eventually, then they will start to cool down. But still, I haven't answered you what is going on, because, well, I have written this expression over here, right? This is very nice. I tell you that I have to consider n0. Now I'm saying the following. Look, the transition happens exactly at Tc. And how I find this Tc? I say, well, exactly at Tc, this function, f3 halves, is exactly 1. Right? So I basically am saying, well, put fugacity equals to 1, and then everything falls down. Everything becomes normal. But when I'm looking on this behavior, so for any, I can put fugacity equals to 1. So this is a very specific value, right? This is a very specific value. This is 2.614. This is some specific value of lambda t. Volume is fixed. G0 is fixed. So this is a fixed value. But when I put fugacity in this part, oh, something bad happens, right? It explodes. As you said, it becomes infinite. So how I treat this part? So how I exactly treat this part? I found the condition. I know that something bad starts to happen when fugacity approaches 1. But to take exactly this limit, it's some sort of a problem, because this guy starts to explode. Okay? And if I simply put fugacity equals to 1 in this part over here, I will get infinity. Okay? And well, there is no infinite number of particles. We know that the number of particles is limited. So how I treat explicitly this part over here?
Never exactly 1.
It's never exactly 1. Yes. It's never, this is the answer. It never exactly 1. So first of all, okay, let's do the following thing. So we do know that this part over here is not a problematic part. It's a nicely behaving function, so nothing wrong happens to this function above Tc, below Tc. This function, for any temperature, is basically well behaved. Okay? So I can just say the following thing, that n excited, right? This is
The
how it goes.
assumption that the fugacity is smaller than 1.
Yes. But even when the fugacity goes towards 1, nothing bad happens over here. Okay? So I'm saying the following thing. Look, at transition, how I find the transition for me is that the value of this function is exactly as if I put here fugacity equals 1, right? So I can say I take the limit of fugacity goes towards 1, so this is obtains a specific value, right? So this is how I define a transition. So n excited is as follows. So when t is above Tc, it is simply G0 divided by multiplied by v, lambda t to the third, f3 halves of the fugacity. Okay? And t below Tc, it is G0 v lambda t to the third power, f3 halves out of 1. Okay? Because I'm saying the fugacity, but something wrong happened or something happens at the transition. And how I define the transition is when this function approaches this value, this is the limit. But when I continue to cool down the system further, this function cannot grow. But this means it stays exactly at specific value that it got there. Right? Something happens to the prefactor because there is nothing wrong with the prefactor. Okay? But this function cannot grow anymore. So it approaches a specific value at the critical temperature, and after this value, it stays flat, right? Okay, so what I do know that exactly at Tc, excited equals to n. Okay. This is also what I know. How do I know this? Because I'm saying before I approach this critical transition, all my integration was perfectly fine. This means that the number of particles that are sitting in a specific level, the measure of those particles compared to the total number of particles is basically 0. So there are some particles living on level 1. But because I'm using a continuum approximation, I'm saying the measure of those particles compared to the total number of particles is basically 0. Why? Again, because n is of the order of Avogadro number. So the number of particles that are actually sitting at level 1 can be large, but it's extremely small when I compare it to this number over here. So what I'm basically saying that the value of n excited, which is the total integral, is pretty much as the total number of particles. Okay. So below TC, so I can say that what? That n is G0 V divided by lambda Tc to the third power multiplied by F3 halves to 1. This is the total number of particles that I have inside my system.
Why TC?
At Tc.
Oh, FTC.
But if it is the total number of particles at Tc, remember what I'm saying that I'm not changing or modifying the average number of particles inside the system. So if it's true for Tc, it's true for any temperature. Okay? The total number of particles inside my system, the average number is fixed, is not changing as the function of temperature. Fugacity can change as a function of temperature, not the total number of particles. Right? So remember, I obtained that the average number of particles is what? Is a function of temperature and fugacity. Right? Now I'm saying, well, we can look on the other way around. Let's fix n and we control t. So fugacity, okay, is some function of n and t. I fix those and it gives me some specific fugacity. Right? And now I'm playing the game. I'm modifying the temperature. I'm keeping the temperature. I'm keeping this number fixed. This simply means that the fugacity is modified. Right? So usually I'm keeping n fixed. So because n is fixed, this expression is true not only for t equals to Tc, equals n equals to G0V lambda Tc to the third F3 halves of 1 for any temperature. So I now can calculate what is n divided by what is n excited divided by n for t lower than Tc. What happens over here? I have to take, where is this guy? I have to take this one, okay, and divide it by this guy, right? So it equals to what we have over here. G0V lambda t to the third f 3 halves of 1 divided by G0V lambda Tc to the third f 3 halves of 1. It equals to lambda t c, right, to the third divided by lambda t to the third. What is lambda t? We erased it, but it depends on temperature. So lambda t 1 over lambda t was a square root of mk Boltzmann t divided by 2 pi h bar squared. Okay, so this means that all of this is t divided by tc to the 3/2. Now I can go and say, well, you see this limit over here? This is a problematic limit because, well, fugacity goes exactly to 1. This guy explodes. How I treat this? I don't really know how to treat it. Okay? But this behavior, or simply this behavior, tells me exactly what n0 is. Why? Again, because I'm saying the total number of particles is fixed. Right? So, if I'm looking on n minus ne, right, divided by the total number of particles, it is simply n0 divided by n. So this is the fraction of the particles that are sitting at level 0 divided by the total number of particles inside the system. And this total number of particles is very, very large, 10 to 22. We know that for t above Tc, this guy goes to 0. Because the number of particles at 0 level compared to the total number of particles is extremely small. Okay? Because we use this continuum approximation. There is a small amount of particles there, small compared to n, and it's actually negligible. Right? So this is t above Tc. What happens for t below Tc? Okay? So instead of using this expression, which is a problematic, I don't know how exactly the fugacity is changing. Right? I know that fugacity is changing because the temperature is changing. I don't know exactly how. So what I do, I use this expression. Because Ne divided by N, I know what it is. Right? So this guy equals to 1 minus Ne divided by N, which is 1 minus T divided by Tc to the power 3/2. This is N0.
N0 divided by N.
N0 divided by N. Thank you. So let's plot this function. This is why it's called also a critical transition. Let's plot this function. How it looks like. So if we plot as a function of temperature, N0 divided by the total number of particles. Okay. We know that there is a critical temperature, that something starts to happen over there. Okay. And we also know that above the temperature, the total number of particles that were sitting at this specific level was simply 0. Right? It wasn't 0, it was 1, 2, 3, 5, 7, 200. Right? Many particles. 200 is a big number maybe. But compared to 10 to the power 22, it was 0. Okay. So this is why what we have, and this is called a thermodynamic limit. We take our system to be very, very, very large. So the number of particles, the number of states in our system is very extremely large. And in this thermodynamic limit, even if we have a finite number of particles that are sitting at the ground state, compared to whatever the size of the system is, it's negligible. We can always say that there is a Tc, and above Tc, there is a limit, or not limit, there is absolutely 0 fraction. Okay, we're talking now in fractions, 0 fraction of the particles that are sitting in this level. What starts to happen above Tc? Above Tc, we have this function over here. So it starts to grow, or square root, and it goes towards 1. something happens over here. Now, it's not momentarily that all the particles are just jumping to if you have this expression called I go below TC, and all the particles immediately are sitting at the lowest level, right? This is what we seen in phase transitions, an abrupt and large change. All the particles were spread at somewhere, phase 1, and now all the particles are sitting at the lowest level. No, it's not what happens in the system. The fraction of the particles at exactly TC is still 0. Okay? And it starts to grow, so it's 0, 0, 0 all the way around, but it starts to grow as we cross this limit. It starts to grow as a parallel. Okay? This guy is 1 minus TC to the 3/2. Okay? So it starts to grow as a parallel, and it reaches 1 point. So all the particles, exactly all the particles in the system, are sitting at the lowest level, only at 0. For any finite temperature, there are still a lot of particles that are spread around. Okay. So we see that there is some sort of a phase transition. And it's called Bose-Einstein condensed state. Okay. And this is a normal phase, normal state. And what we see is that there is a transition between a normal state to a Bose-Einstein condensed state, but the transition is smooth. Remember, so all the phase transition that we covered at the first part of this course were abrupt phase transition, right? So you look on the water and you cross the critical temperature or you cross the critical pressure, and then the volume suddenly jumps, right? And all the system becomes something else. Here you cross the temperature and a part of the system sits on this whole level, not the whole system, but a macroscopical part. It's still a very big change, but it's a smooth change, right? It's not that we crossed over here and then we had an abrupt jump. No. So this value, this fraction, is smoothly going from 0 to something else. But something indeed diverges. So what is going to diverge? The derivative, right? So the derivative of this value, n0 divided by n, is going to diverge at this point. The derivative here is 0. The derivative here is something else. Okay? So the derivative itself is somehow diverging exactly at this point. There is a jump in the derivative. Okay? We will discuss it in a minute. So basically, this is what happens for bosons. We treated all of this mathematically, and we do understand that below TC, macroscopical part, not the whole part. In order to get all the particles at the 0 level, you have to go to 0 temperature. But macroscopical fraction of all the particles, and there are a huge number of them, is simply staying at the lowest level, and there is nothing that we can do about it. Okay? This is the physics. If we want to compute other stuff, okay? So for example, if we want to compute what happens to the energy, or what happens to the grand canonical potential, right? Because we now only have an expression for n, right? We know how n is behaving. So this is fugacity 1 minus fugacity plus g0v divided by lambda t to the 3 f 3/2 of this guy. Okay? Now, how exactly to treat this, and from here to obtain what is the behavior of the grand canonical potential. Okay. So we know that this part, this is we already showed, that this part is going towards G0 minus G0 K Boltzmann T F 5/2 of the fugacity. This is how we obtain this guy. We basically have taken this function, performed the derivative, and obtained this guy. Because remember, n is minus d psi d mu. Oh, there it is. Lambda t.
So
Now-
from an integral.
Yeah, we perform an integral, and only on this part. Okay? Only on this part.
Stas, inside the lambda t, there is also t.
Lambda t, there is also t.
So if you
Yeah,
do
over here,
integral-
there is lambda t and k both on t.
Okay, but if you do integral in the
But I to take this derivative of this guy with respect to mu, not with respect to t. Okay? With respect to mu.
I have a question.
Yes.
At the beginning of the course, we said that when we look at a function that depends on some variables, it's not enough to look at the integral just on mu. We need to look at the integral of other values too.
Yeah.
So why can we say that psi equals to minus integral and
We can.
v mu?
We can. This is exactly, so you know how to take this guy and to take a derivative while keeping t constant, and we obtain, if you take a derivative of this, you will obtain this expression.
Yeah, but if we will look, אם אנחנו נסתכל על נגזרת השלמה של פסאי, אנחנו נקבל גם תלות בנגזרת לפי t ולפי
Of course. But what we assume, so you're asking the following question. If we take a derivative of psi with respect to df, d mu, we will get a different answer than taking d psi to d mu.
Yes.
Okay? So how I'm trying to treat it. So if I take the derivative of psi, a partial derivative of psi with respect to mu, I will obtain this expression. So this connection is fine.
Yeah.
Okay? I'm saying there is also something else that I don't really know what it is. Okay? That when I take a derivative of whatever else is here, I have to obtain, okay, something that looks like this. That's my claim. I don't know what it is, but I'm saying it's an additive to this guy. You can say, well, maybe there are some other constants that do not depend on mu. But if they were independent of mu, they were be sitting exactly in this function.
Why?
Because you see, the only problems that we had are when fugacity were going to 1. Okay? Anything else that were independent of fugacity was behaving normally. The problems that we had was only from the one specific energetic level. So we need to treat this energetic level properly. Everything else was treated correctly.
Yeah, but how do we know when we... איך שאנחנו עושים אינטגרל על n, שאין לנו חלקים שנגזור אותם?
Well, okay. So I'm saying the following thing. It's a good question. So if you remember how we started, we obtained that psi was minus 2/3 g0 v 2 pi squared, right? 2 pi squared 2m divided by h bar squared to the power 3 halves, and then we had an integral between 0 and infinity, epsilon to the power of 3 halves, divided e to the beta minus beta, I think, beta epsilon minus mu, minus 1, d epsilon. And we obtained this, so this is the full function, okay? The full function as it described, okay? And we found out that something bad was happening when we look on the zero energy. So the whole problem in this integral was when epsilon going to 0, there is an additional delta function over here. Okay. Now, all of this is correct. So the only thing that is left is what happens with 0 equals 0, epsilon equals 0 level. That's the remaining question. Now, I'm saying the following thing. All of this is exactly this. Right? And it stays the same. Now, whatever was the addition to this grand canonical potential, there is something in addition, because this integral stayed correctly, it was fine. There is something, okay, some additional function that described this psi for the ground state level. And we know that if we take only this something, take a derivative with respect to mu, we obtain this guy over here. This is my only claim. So I'm saying that it can be dependent on temperature, it can be dependent on something, but all of what is missing is something that contributes to this part over here. So the only thing that I need to make a connection or correction is to find this square that I don't know what it is, and I know that it produces this form. Okay. This is the only claim. I'm not taking the whole integral, or I'm not taking the integral of psi with respect to mu of everything. I'm just saying what psi, okay, could be here that will produce this behavior over there. And I can treat it simply by either taking an integral or looking what happens at the ground state level. That is because the only thing that matters is what was on the ground state level. Okay. And what was at the ground state level? How the psi was obtained. So you remember, what is, if I'm looking of F0, okay? If I'm looking of F0, so it equals to minus 1 over beta multiplied by log of 1 minus e to the power 1 over e to the power minus beta mu minus 1. Okay. This is fine? This is a partition function.
Yeah.
This is the grand canonical potential of a single level. Right? So I don't have to make an integration of this guy with respect to mu. I can go to this zero level because the only where this came from the zero level. So I'm going to the partition function of the zero level, or the grand canonical potential of the zero level, and I write it down explicitly. Okay. Now, moreover, because there is also a degeneracy, so I have to add G0 over here, okay? Because the levels can be degenerate. Okay. So when I write it down, and I remember that I have also a fugacity over here, what I obtain is G0 K Boltzmann T log of 1 minus fugacity. And that's it. So my
Why is it
total,
supposed to be fugacity in the power of minus 1?
because minus 1. Sure. So it is fugacity minus 1 minus 1.
Yeah.
So now, psi, total psi, is G0 K Boltzmann T log of fugacity minus 1 plus minus G0 K Boltzmann T divided by lambda T to the third F5 halves, so this is Pauli logarithm of 5 halves of the fugacity. This is the total grand canonical potential, right? And we can use it always, no matter what the temperature is. Right? The only thing that we need to remember, and you will see it in your TA's exercises, that you see this is a problematic part. It is as for n, right? We had fugacity 1 over fugacity, and then we have plus G0V divided by lambda T over to the third power F of 3 halves of the fugacity. Okay. And how we find for the number of particles this guy. Okay. So usually what we do, we say, well, we know what happens at Tc for this part. We know what happens to this part at the critical temperature. And we find this part by taking the difference. Okay. The same happens at the for the ground canonical potential. We know that this behavior is fine. We find it at Tc, and then we just simply subtract it, and that's it. Okay. So in order to treat what happens to the ground to the ground energy level, right? We treat all the excited states. We compute, and then we compute the difference from the total ground canonical potential minus the ground canonical potential of the excited states. Right? You will see this in exercises. So this is basically what we need to know about Bose-Einstein condensation. And it's a fantastic phenomena on its own. But it brings us to this very interesting transition over here. Okay? Because if you remember, phase transitions there were extremely nice behavior over there. But as I mentioned already today, phase transitions, the changes that we have seen due to the phase transition were extremely abrupt. So if I will remind you, for van der Waals gas, if we plot the volume and we plot here temperature, so we once obtain the following plot. What is this plot? This plot is for a specific temperature, which is a critical temperature. We shift the pressure a little bit, and the gas, so this is gas, this is liquid. Okay. So remember, we found by using, for example, Maxwell construction, we find a critical temperature and a critical pressure, such that if we increase the pressure a little bit, the system jumps from one volume to another. And here we're forbidden state. So the system never sits here, right? Because equilibrium cannot be achieved. And we know that when we sitting in this for the specific volume, specific temperature and specific volume V0, if we at this point and we increase an external parameter, we increase it a little bit, the system, this is the phase transition, the system was jumping from one volume to another volume. This is V1. Okay. And those were our phase transitions. They called discontinuous phase transitions or first order phase transitions. Any situation such that you change your parameter, external parameter, and here was the pressure, you change it a little bit, and the system performs a huge jump, so the total volume of the system was V0, and now it's V1. It's not an infinitesimal change. This is something very interesting about the phase transitions. It's a macroscopic change, right? But and the jump where you start and where you end was described by this red curve. And the lower your temperature was, the larger your jump was in the volume. But if the temperature was low enough, okay, so if this was your temperature, so your starting point was here, and eventually, if you increase your pressure a little bit or decrease your pressure a little bit, you will jump in this other volume. And there was a specific point over here. Okay? We can call it Tc. And what happens at Tc, okay, if you remember this isothermal in van der Waals gas, what happens in this Tc, there is a critical point. Okay, there is a critical temperature, you change your pressure a little bit, and you going from liquid to gas. So here you're liquid, you change your pressure a little bit, so you're shifting a little bit, and you're now in a gas state. Okay, but there is almost no jump, right, in the volume. So the total volume of the system remains the same, because you see this red curve basically is not going to infinity. There is a limit over here. So if you're sitting over here and changing the volume, the pressure a little bit, you're still sitting over here. So there is no modification of the total volume of the system explicitly at this critical temperature. Right? This is already not a discontinuous phase transition. It is related to what we see over here. We change the temperature somehow, and there is a critical temperature such that at this temperature, the behavior of the system becomes different, right? So this is a condensed state. Huge number of particles are sitting at the lowest state of the energy, and this is a normal state that, well, they somehow spread around. And if you're exactly at this point, everything looks continuous, right? Nothing bad happens in the system. No jumps, no abrupt jumps, right? Exactly as in van der Waals at this critical temperature, when the system goes from one phase, which is liquid, and it can go to a gas, but the volume of the system remains the same. Okay. So this transition at this point, called continuous phase transition, continuous phase transition, and also here it's a continuous phase transition. This is a class of phase transitions which are called second order phase transitions. And this is the phenomena that we're going to be interested in observing, solving, describing explicitly for magnetic systems, but not only for magnetic systems. And this is what we will continue to develop next week. So we are starting a new chapter, which is second order phase transitions in magnetic systems, right? And it's related to what we already seen in the van der Waals at explicitly one single point, or the Bose-Einstein, again, and explicitly one single point. But as people figured out, it seems not really important, right? Here is a lot of many transitions, and this is some special point. Who cares about one single point? But it actually defines huge number of properties of the system, because some singularities are hidden inside this point. Very exciting and new physics. See you next week.
Right,